Hey there, you right? So I can see that there's a question here for 10b. It's actually a really good question. How do you convert recurring decimals into a fraction and percentage? It's not something I focused on in terms of proving and showing. So this is a great question that you're asking. Decimals, when it's recurring, I'm assuming it's not the decimal to percentage that you're asking, because essentially you can still do this problem. 0.3 recursive is the same thing as saying 0.33333 carrying on, and I'm assuming knowing how to change it to percentage simply by multiplying by 100 to any term will convert it into a percentage. And we know that when you multiply by 100, we're moving the decimal point forward twice, and that gives you now 33.333 recursive percent. So likely you would have figured out that, yep, I know how to do 0.3 recursive into a percentage, and likely this would be 66.6 recursive percentage and 99.9 recursive percentage. Technically, you can also convert that into a fraction as well, which is equivalent to 33 and a third percent, and this would be 66 and 2/3 percent, and technically this is 100%. But we'll talk about that once you understand how to convert decimals to fractions. Now, there are two ways to do this. One is the actual proof to why this technique works, and one is just how to do it. Now, if we were to just do it, right? If we were just to do it, then this is the technique. I'm going to quickly show you. And there is a link that I'll attach as well for Khan Academy, where he tries to explain this a bit more if I'm going too fast on this. But essentially, the shortcut in understanding how to do these is simply, what's happened here? Is simply to divide them by, and I'll show you here. Let's see, 0.3 as a fraction, 0.3 is the same thing as writing 3 out of 10. Now, because it's recursive, technically it means that they'll continue on with these extra 3's, whereas 3 over 10 only gives you 0.3. The trick here, or the technique, is that you divide it by 9 instead. So if you changed it to 3 over 9, then it will give you that recursive decimals that you're missing. So technically you would write 3 out of 9, which is 1/3, which is equivalent to 0.3 recursive, which is why we know over here, if this is 33.3 recursive, you can change that to 1/3. Okay, now the question is, why can you just divide by 9? Well, and I'll just answer these questions here. So 0.6 technically would be the same thing as usually writing 6 out of 10, but we're now going to write it as 6 out of 9. Okay, and then same thing here technically, and this is where it gets interesting. Technically this would be 9 over 9, which is actually 1, which is why we write 99.9 recursive percent is the same thing as 100%, and that takes it to another level of understanding where we talk about limits and I guess approaching a particular infinite value. That's a bit much deeper. So if you're interested, you can try typing in Google the 0.9, does it equal to 1 or not, and there'll be sort of an article to sort of explain that concept. But just for the argument's sake, for this session, if you're asking how do you convert it to a fraction, it's simply dividing it by 9 instead of 10, and that gives you 2/3. So you'll see here, if I just go to my calculator, that's just another different type. So 3 divided by 9, you can see that's the 0.3 recursive. 2 divided by 3, or 6 divided by 9 is also the same. It's 0.6 recursive. So to convert this is technically 9 over 9, which is equivalent to 1 on a technical basis based on a sort of a limits of approach concept. Now, you can stop the video here if that's all you wanted to know, how to convert recurring decimals into a fraction. You simply divide them by 9. So it'll be the same if it's 0.7 recursive, that would be 7 over 9. So you can see here, if I just did 7 divided by 9, you also get 0.7777 recursive. Okay, so that's how you would do that if that's what you're interested in. If you're wanting to know how the technique works, well, this is the theory. Okay, you can pause the video here if you wanted, but if you want to know the long method, 0.3 recursive is the same thing as saying 0.3333333, right? It goes on forever. Now, the thing is, we want to know what it is as a fraction. So we don't know currently what fraction that equates to. So we give it a number, and with that fraction, we call it x. Okay, so if x equals to 0.3 forever, right? Well, then we want to know what x is. So what they've found is a trick, a mathematical logic, a logical concept is they said, well, what if I decided to do 10 times x? Meaning, whatever 0.333 is, if I decide to say, let's times this infinite decimal by 10, then what would that equal to? Well, based on that concept, when you divide times by 10, remember, you can just move the decimal place one place value forward, which actually changes this to 3.333333 recursively. True? Now that's interesting because this is what we have here. Together, x is equal to 0.33 infinitely, and 10x is equivalent to 3.3 infinitely, or 33 infinitely. So what if I then said, if I took 10x minus x, that's the same thing as saying 3.3 recursive minus 0.3 recursive. True? So what does that mean? Now 10x minus x, we know that's equivalent to 9 of these x's. True? But then what's 3.333333 infinitely minus 0.33333 infinitely? Have a think about it. If I wrote it out much more clearly for you, 3.33333 all the way minus 0.33333 all the way. What does that equal to? If I told you to minus this, what you would have said is 3 take away 3 is 0. 3 take away 3 is 0. And 0, 0, 0, 0, 0.3 take away 0 is 3. True? So that means when I say let's take 10x, so take this number, take away this number, so 3.3 recursive, take away 0.3 recursive, it should actually equal to just 3. True? Now, if this is true, if this statement logically makes sense to you, if that is a true statement, this is beautiful. You see, right here, you're saying 9 times x, which is the number or the fraction that we were interested in the beginning. True, we wanted to know what x equals to because that's the fraction to represent 0.333. And so what's interesting here is that if 9 times something equals to 3, well, how do you work out that something? Well, we do the opposite. This is what year 7 mathematics was. Instead of timesing by 9, see times 9, we can do the opposite of times 9, which is to say divide 9 on both sides. See, divide 9 and times 9 are inverses of one another, and so therefore x will equal to dividing 9 on both sides is the same thing as 3 divide 9, which you can write as a fraction as 3 over 9, that's why we can say that is 1/3. So if x as a fraction is equal to 1/3, which is over here, then we can now say 1/3 is the same thing as 0.33 recursive. Okay, and that's where it's interesting, this whole idea of dividing by 9, which is this step here, that's where it comes from. Okay, if I've confused you with this abstract conceptual understanding, then you can just memorize the technique, which is to divide 9, or you can try to sit there and ponder for a bit and wonder if this statement is true. If this statement is true, then do you understand this algebraic component? So if you're having troubles understanding this step here that I'm showing you over here, then another way of thinking about it is if I did magic squares. 4 times something equals 12, right? Now we all know the answer is 3. But another way of doing this instead of going through your times tables is you can think of it as, since you times 4 to get to 12, so you started off with 3, this is what you started off with, and you times it by 4 to get to 12, then another way of doing it is, well, what if I then said, reversing it, 12 divide 4, or I divide 4 on this side, 12 divide 4 should give me this number. True? So let's think about it. 3 times 4 gives you 12. But then that also means 12 divide 4 should give you 3. True, because you're just inversing them. So times 4 to get here, divide 4 to get back, right? So you can see here, watch what I'm going to do here. I'm going to do it on my CAS to prove you my point. I'm going to clean this slate here. Think about it. 3 times 4 is 12. 12 divide 4 is 3. True? So that means as long as I do the inverse of times 4, which is the opposite of times 4, is divide 4. So that means I can do something like this. 5 times 66, right? Is whatever it is. But if I take that 330 divided by 66, I should get 5. True? So if you times 66 and then you divide 66, you should end up with the same number that you started off with. So think about it. What I'm trying to say here is that if I said 5 times 66, right? Whatever this answer is, doesn't matter. Take that answer and divide by 66, you should get 5, right? So as long as you do the opposite, which is times 66 and then divide 66, you should end back with the same number. So this is where it's interesting. With our problem before, we had 9 times something is equal to 3, right? And so to work this one out, all I said was, well then, to find out that magic box there, that magic box is equal to 3 divide 9. Can you see what I'm doing there? I'm just saying, since I said times 9, I'm going to do the opposite of times 9. I should do it this way. It should be something times 9 is equal to 3. Well, then the opposite of times 9 is to divide 9. True? So I take the final answer and divide it by 9. That should give me whatever is in this box here. True? Just like how I did over here. 5 times 66 gives me this question mark, right? Whatever this question mark was, if I just divide by 66, I should get the original number, which is 5. So I'm doing the same thing here. I did magic box times 9 gives you 3, and if